what pattern is required to find weaknesses in the product. But they have usually no know-how of the tester itself. But in today's world, signal integrity, we'll talk about it. It's also a key know-how that you understand the tester. So in my opinion, those three know-hows have to come together that you can seriously develop a memory tester and talk about test. Also, our target is to be in symbiosis with the big suppliers, Samsung, Hynix, others. We are not competitors. Typically, a wafer supplier is a competitor, so only sees his own technology and products. Where if you want to do powerful testing for your customers, you must be able to understand all technologies. So this is where our different sub-companies or business units come in, a strong distribution business giving access to a lot of end customers. An own memory brand to have the know-how of the DRAM itself, and then Neumonda Technology being the tester company, what we will talk about. And all three together we call Neumonda Group. So these are our three business units. And let's dive now into memory testing. So this long nose here is me being in a conventional backend. That's typically how a backend looks like. This is a handler where you stock your DRAM, and then the handler is simply transferring the memory component DRAM, or for other volume testing, you have similar equipment, onto the test head, provide the right temperature, and do the testing of the circuits. You can see this was after move in of the tester equipment into a small backend. Typically, these are the mainframe units. Then you cannot see here test heads coming out. The test head is then part under the handler, because the handler must be put over the test head of the tester mainframe to move the memory components to the tester and do testing. Typically, two handler for one tester mainframe, because you have two test heads for higher throughput. This is an aisle of burn-in tester. We will talk also about this later. So you can see pretty heavy equipment, 3 tons, 3 tons. If you want to do volume memory testing, you need significant equipment. So let's talk about DRAM testing today. The minimum you need if you want to test any semiconductor memory is a burn-in test system. Then after burn-in testing, very high temperatures, you move to what we call array testing. For this, you need a tester, typically with 2 test heads, and then a related handler. The handler would be moved above the test head, and the handler is then moving the components there and away. This array testing you typically do twice. At high temperature, then you move the memory components out, and later you move at low temperature. After this, you go to speed testing. This is a typical speed tester. They're very expensive, so frequently only with a single test head. Handler again. Then you do a speed testing. Is your memory circuit working at speed? For highest quality, you also do it at 2 temperatures, high temperature and low temperature. So 5 test insertion before your DRAM is finished. In addition to the tester mainframe, test head, and the handler, you need some other equipment, change kits, high fixes to handle your specific DRAM. We will talk about this later. So minimum, if you want to do DRAM testing, would be 1 burn-in test system, 1 array test system, 1 high-speed test system, 15 tons of equipment. Even if you only use a single test head, $10 million invest. And if the equipment is running at full speed, also quite some power consumption. Talking 200 kilowatt of power consumption of this equipment running. So let's go through those different steps. Why are they necessary and what's happening there? So this is a typical burn-in test system. You slide open the door. Then you have boards with sockets, and the memory components to be tested are inserted in those sockets. Very high parallelism, maybe 300-400 pieces. Then you plug this board with this connector here into the back of this test system. You stack maybe 20 boards above each other, left chamber another 20 boards. So a complete lot of memories, couple of thousand pieces you can test in a single test system. The purpose of burn-in testing is to age the parts. So you want to catch infant mortality issues. You try to simulate the first 3 to 6 months of customer life of your DRAM component to find infant fails. Then typically, if you have done burn-in procedure properly, then you have stable fail performance over the lifetime of your semiconductor, typically 10 years. Then you get wear out. Then your technology is wearing out. Your silicon oxide of the transistors is damaged by the constant bombardment of electrons, and then the fail rate goes up. So the purpose of burn-in is to simulate the first 3 months of lifetime to find any weaknesses in your circuitry. The board's pretty long, 60 centimeters. So the electronics is all hidden behind. So you have very, very long signal lines here. How can you simulate age your part 3 months or 6 months of lifetime with a test that lasts only typically 4 to 10 hours? You need acceleration. This acceleration of semiconductors you achieve by temperature and voltage. So you operate it at much higher temperature than usual. So 125 degrees. No customer is operating the DRAM at 125 degrees. So in burn-in testing, we raise the temperature to very high values. That gives you an acceleration factor of 10, 15, and we increase voltage. If the external voltage, supply voltage is 1.5 volt, maybe you go to 2.5 volts to stress your semiconductor, the silicon, any weaknesses. That gives you another voltage acceleration depending on your semiconductor properties, 10 to 20. So those two factors combined give you a very strong acceleration factor. And then in a 10-hour test, you try to simulate 3 months of lifetime. For this, you need secret test IP. If everybody today in semiconductor technology usually using voltage generators, though the external supply voltage does not get into the inside of your silicon. So you need to switch it off. So you can only do effective burn-in if you are the designer or manufacturer of the memory and can switch off some of your semiconductor features, or you cannot stress the part. Also, because you plug many components on a single board, you have to share signals and you have to do compression. If you have, for example, 16 IOs in one DRAM, you try to compress the result onto one single IO so that you can operate as many as possible. This, again, needs secret test IP. So usually, if you get the memory component of somebody else, you're not able to do this burn-in test. Because the memories are exposed to very high temperatures, 125 degrees, the electronics of the tester must be protected from it. So it's hidden behind and it's far away from your memories. So you cannot operate at very high frequency, maybe 5 megahertz in typical burn-in systems. They try to increase it now to higher frequencies. There are systems where you can operate 50 megahertz, becoming a stretch at those long signal distances. The motivation is it's a relatively cheap test system at $500,000 to $1 million US. So you want to move tests from the later, more expensive test system into the burn-in oven. That's why they're interested to provide higher frequencies in these burn-in equipment, so you can move tests from the expensive test equipment to this cheaper test equipment. Has nothing to do with real burn-in stress. This is called test during burn-in. So after burn-in procedure, you go to array testing. For array testing, you have a big, relatively expensive tester, $2 to $3 million with two handlers, very heavy, 8 to 9 tons, consuming maybe 100 kilowatt of power. And here you try to test the memory DRAM cells. So you also try to make it highly parallel. This is a view on the test head here. You need a high fix to configure, to connect the tester to your specific circuitry, depending how many IOs or pins you have here. They have to be connected to the right resources of the tester, addresses to address drivers, IO to IO receiver and drivers. For this, you need a high fix. Also, very expensive, up to $250,000, long production times, design times for a high fix. Then you have the handler. Handler also needs precision mechanics, maybe $50,000 for a change kit. So depending on the physical dimensions, length and width of your memory package, that the handler can grab it and move it onto the test head here. Also, if you change the handler from one component, from one DRAM to another one, you need to stop it for 2 or 3 hours to mount in this change kit for the new device size. So not so easy and quite complicated to do DRAM testing. The purpose of this array test is only to test the memory cells. An 8 gig DRAM with 8 billion memory cells. You travel through all those cells, ensure certain environment around this cell. If you want to test for leakage, depending on the leakage mechanism, maybe a 1 in the memory cell and zeros around it to stress cell-to-cell leakage. The problem of array testing is it's also highly parallel. So you have relatively long transmission lines from the test head to the DRAM, so you cannot operate it at full speed, 300 megahertz only typically today. So maybe in your application, the DRAM operates at gigahertz, but on the tester for array testing, you can only operate it at 300 megahertz. Signaling very ideal, no noise, good tester environment. You also work with compression to test more in parallel because this tester is very expensive. So also IOs you typically compress. So you also need a lot of secret IP, and only the manufacturer who designed the DRAM can typically also test it. Because it's an ideal environment, this is a typical sensing process of a DRAM. You get a tiny signal internally, and then you try to read and amplify it. Or if you have a 1 stored and now you want to write back a 0, it needs a certain time that you get this signal from the internal onto your bit line into the memory cell. And this is heavily influenced by noise. If, for example, the ground here is bouncing because the DRAM is very active and working in a noisy environment, it will be slower. Such effects typically cannot be found on a tester where everything is ideal. They use compression that not all IOs are active. So it's very difficult for an array tester to find a lot of weak memory cells. So also the DRAM manufacturer provides secret test modes. For example, if you have a spec write window of 50 nanoseconds, then you shorten it to 12 or 11 nanoseconds, hoping this way you can find weak cells, which the tester itself cannot find. But later in application, when you are running in a noisy environment, you need to find those weak cells. So also a lot of tricks used here to find weak cells. So change kit, high fix, very expensive. I mentioned it. So it's only worth for very high volumes and takes long lead times. If you have a new package size, it takes you half a year to get change kits and high fixes for it manufactured. So after array testing, you go to speed testing. The most expensive tester today, $5 million US, also consuming a lot of power. Because so expensive, typically only a single test head, not as much parallelism, because in final speed testing, you need to activate now all I/O. You must make sure that your complete memory semiconductor is functional, so all I/Os must be active. Here you test at gigahertz, less parallelism. You can test at very high precision, up to 20 picoseconds of such expensive test equipment. Again, very ideal signal integrity environment. Because the tester is so expensive, you can only afford typically 30 to 60 seconds of test. The array test before, a little bit cheaper, typically 20 to 30 minutes. So a lot of test effort burn in. Array test, low temperature, high temperature. Speed test, low temperature, high temperature. With all this high complexity and investment, still customers complain the quality is not good enough, especially in module business, with ECC, with error correction. The servers notice if there are single bit fail events. So you get a lot of feedback about still there are sometimes single cell fails. There are still signal integrity issues. The DRAM boots maybe 1 or 2 or 3 or 4 times. A 5th time, the server or motherboard cannot boot. So this is the reason why a lot of companies, in addition, in their backend, are doing motherboard testing. Yeah, here I show a little bit primitive version. It looks a little bit better in the factories, but basically you use an application, a motherboard, you have your memories in there, and then you put a climate chamber above it. This is a little bit manual version, and it looks not so good because this is a cold temperature climate chamber connected with a thermostream. And then you can test in the application at low temperatures down to minus 40, 50 degrees, or at high temperatures, typically 50 to 80 degrees. So this is the module in such a climate chamber. You have a little bit parallelism, typically 4. And here you already see some problem of this module testing. With low temperature, it's very nasty because the cold air has to get out somewhere. Many backends are in Asia, high humidity of the environment. You get icing, very, very, very nasty. Therefore, this motherboard testing is typically only done at higher temperatures and typically only for modules because it's manually plugged, not really good automation around for this. Then the operator puts on a microclimate chamber, then you test it for 20 minutes, and then you take it out to improve quality. Difficult for component testing because then you need such clamshell sockets. You have to plug them in manually. Then it's like a memory module. Then you plug it in and test it. So for components, not really a good solution. But this motherboard testing needed to improve the DIMM module quality. So you see, lots of efforts, multiple insertions, which is also not good for quality. Each time you touch and put a component into a socket, you potentially damage the walls. So this is why we came up with a very different approach. Try all in one. So we developed a board where the electronics is at the bottom, protected from the severe temperatures of testing, minus 40, 50 to plus 125 degrees. Then we have an insulation layer in between, and on top we mount PCBs, for example, with component sockets. You can also put your memory DIMM module slot, so the same way you can test also memory modules. So now the bottom is thermally insulated from the top, and you can put the top in a harsh environment. But your controller driving the memory channel is very close to the components. So you can go now at full speed. It looks like a burn-in board for classical burn-in, but this is not performing at 5 megahertz. This can perform at gigahertz. So here's a microconnector, how you go up. And it rebuilds application. It's not so clean in signal integrity like a tester because it more rebuilds the memory channel on a motherboard, even a little bit poorer because the distances are longer because of the DRAM sockets, but that is good. That provides guard bending. That makes it signal integrity poorer and more rebuilds a customer environment. In this version here, we use an FPGA to drive the signals. Then you plug the whole board into such a temperature chamber. It moves in the bottom, it is cooled. The electronics is protected. The memory components can be exposed to any temperature desired. So you achieve high throughput, almost 200 components you can load, high parallelism, but all are fully operated at gigahertz with all I/O connected. A more customer application realistic environment. You mount several on a board, and then you can use the infrastructure which exists today for burn-in. Automatic loading, automatic unloading, analysis of your test results, when are the sockets degrading, when you need to replace it. Instead of a $250,000 high fix, our high fix is now this printed circuit board. Can be designed very quickly, 3-4 weeks, $5,000 development cost, very cheap. If you have a new product, different size, you need a new socket, or you want to plug in a memory module, or you can even think of flash testing, SEDs. You just redesign it, you redesign your application control, and you can relatively configure and redesign the tester to totally different products. So instead of tons of equipment, you have now 10 kilograms, this board. Maybe $10,000 production cost, so 1,000 times less than this professional testing equipment. Low power consumption, 100 times less. Very quick turnaround times if you have to adjust to new products. So a quantum leap in handling testing and test invest cost. Because it's cheap, you can test now for 12 hours instead of minutes. That brings quality. So we are convinced after the experiments we have done with the first prototype, even quality will be better than in a classical testing approach. So one big question is, how do you control now your memories? How do you test them? Do you use an FPGA or do you want to use a CPU or more motherboard based? Both have advantages and disadvantages. The platform with the FPGA we call Rhino family. Rhino because it's a heavy, big, like rhinoceros FPGA, and River Rhine because we developed it in Germany. So therefore this funny name. The beauty of FPGA is you can completely control the pattern, how you test your memory. Because for DRAM, for some technology-related issues, you need a very specific pattern. If you do motherboard testing with a CPU, there is a microcontroller, the memory controller, controlling the memory channel. So the pattern you write, you don't know exactly what physically happens on the DRAM. So you lose control of the physical pattern on the DRAM. So with FPGA, you can completely control it. The disadvantage of FPGA is you cannot achieve the highest speed levels. FPGA is expensive and always trails the speed of a motherboard. If you can do a DDR4 4200 on a motherboard, the FPGA can do maybe 2400 speed grade. Or you have to take very expensive FPGAs, but then you're still lacking in speed. But you're very flexible in pattern. So therefore, we started another development based on motherboard, a specific motherboard. We call this Octopus family, where we use a classical CPU, make 6 tiles, the same size of the board as with FPGA, so that the whole infrastructure can be used, MES system analysis, etc. This one, we have already a prototype for DDR3, DDR4 testing lower speed grades, as I mentioned. This is in development, will only come next year. Then we will also be able to do LPDDR4 higher speed grades. And in our final platform, we also want to introduce noise to test for robustness. So 2 platforms, one very flexible in pattern, but not super high speed. The other one, high speed and natural environment of a motherboard, but no pattern flexibility. The first one, we have prototype. This we are using now for internal testing of our own products first. That's how it looks like. The bottom view, the FPGA, 6 identical tiles, top view, 2 dot boards we call per tile, which can be easily unscrewed, replaced, working. The Octopus platform in development, same concept, just you put now the motherboard in the bottom, the memory channel you separate from the motherboard and put the memory on top so that you can expose it to extreme temperature conditions without damaging your CPU. This is the bottom view, this is the top view. You can place component sockets on our what we call DOT boards. Then you can do component testing and don't need those nasty clamshell sockets anymore if you want to do component testing. You can use burn-in environment, loader, unloader for automatic loading, unloading. If you want to test modules, then you simply unscrew and replace it with module slots. Then each of those DRAM component sockets is replaced by a module slot. So both you can do module and component testing. Bottom, the CPU port, then the microchannel going up here, isolation, and then in the climate chamber, you run the memory components, the top side, or the memory modules. This is under development. So if this is done, there's still a lot of challenges. What is the right signal integrity? How much bad signal integrity you want to afford? Poor signal integrity is good because it protects the customer. If you make it too poor, you cut into your yield. So what is the right socket? What is the right performance? What is the signal integrity? What's the reliability of the socket? How many times can you load, unload before it breaks? Do you want to operate with C-springs? What's the inductance? How fast does it degrade? You need to monitor this with an MES system. Automatic load and unload, climate chambers. So a lot of things you cannot simulate, you must simply do. For this, we have set up a pilot factory where we want to use the system first internally, where we have a test flow. It's a little bit complicated than this simplified test flow, but basically you need to automatically load your boards. You do full testing, burn in 125 degrees at speed. We'll talk later about it, why. Then you do go down in your temperature to normal temperatures. You do your full high temperature array testing, speed testing in one set, because we can run our gigahertz. There's no need to separate into an array and in a speed testing anymore. You cool down, you go down to very low temperatures, minus 40, minus 55. You do again testing at speed. They remain always loaded on the board because now the tester is small. There's no need the parts move to the tester. The tester can move now through the factory. That means you load once on your board There's no danger an operator exchanges the part. You touch them only once, and then the board walks through the test factory to perform all those test steps. So very radically different approach than today. And when you are finished with all your test steps, you can afford very long tests now, 10, 12 hours. Then you do the automatic unload and sorting out and then inspect and mark. So this is the pilot factory. We need to also, because you have to do now a lot of volume experiments. We did those experiments before, but without the boards and the automatic equipment, everything manually, very nasty, very interesting experiments. For example, what's the difference to classical flow? Here you take, for example, 10,000 parts are tested with the flow of manufacturer A. Then you take the pass parts, run them through the manufacturing flow of manufacturer B. They had been proven pass in flow A. Now you get failed parts. Then you build modules from all those failed parts, and you're very surprised they all pass if you run them extensively in application. So what is the root cause for this? You can reverse the experiment. First, take the test flow of manufacturer B. You take again all pass parts, then you run the production test flow of manufacturer A. You get the same effect. 2 to 3% are now flagged as fail. You again build modules, run massively in application, they all pass. Very interesting experiments. This experiment proves, we have not enough time to go into detail here, that using this approach, which is more application close, your yield will raise by 2 to 3% if you use this testing approach. Other experiments, you have to compare classical flow with this more application flow. This was an experiment. You do classical motherboard testing, but now on components, and then you get fails. Proven fail, 64 milliseconds at 90 degrees, maybe in a motherboard. Now you plug those fails into a classical flow with this highly expensive test equipment. Oops. And many of those proven fails in application in motherboard are not found by the classical flow. So you can make a lot of cross experiments. What is your quality? What do you gain? What do you lose? And for this, you need a pilot factory, because such experiments need 10K or 20K of components if you want to sort out 50, 100 ppm events. You can do a lot of studies because our tester allows you to pull bit fail maps. This is a typical shared memory cell, the stack memory cell coming down. Then this here, then the selection transistor connecting it to the bit line. They share this contact. If a contact has issues, then typically those two cells fail. So you see a double fail here. Or burn-in experiments. This is a classical fail while you are doing burn-in testing. You want to burn it through at this 125-degree initial burn-in testing, because maybe pass at customer, but after 3 months, it gets lower resistance and then it turns into a fail. So we can test now at gigahertz. We are getting much more sensitive to such issues and can detect them maybe at gigahertz, which you cannot detect at 5 megahertz. So such experiments, you need volume, and this is the reason for this pilot factory. Here you see a word line oriented fail, very typical. You can run out for hours, for 12 hours, things like variable retention time. A memory cell is healthy, an ion moves in your silicon, and after 5 hours, it suddenly fails. Classical testing cannot discover this. For this, you need long test time. Signal integrity. What the socket is the right one. High performance socket, a C-spring socket. How much signal, degrading signal integrity is good for testing? When do you cut into yield? This has to be studied. Certainly our FPGA, our design has to be improved. Patterns can be programmed into the FPGA. So you have to do a lot of work on FPGA design and controlling the memory controller on the FPGA, because you want to make sure what pattern physically you exactly write onto the DRAM, so that you can also do technology pattern testing and verification, which is not possible with this CPU approach. And this is my last slide for today. This is our vision for the user, for the future. We want to be able to take any wafer of any supplier without their specific IP, be able to test it in our environment. The patterns we want to upload on the internet and make available to others, because the hardware we can control, we know who is using it, how it is used. The tester, ideally, we want to make available to other companies. Many companies have a need for this testing. They can use it freely. It's a pay-per-use model for the future. They give it to their end customer. The end customer has any issue, feedback to them. They cannot handle it, feedback to me. We improve the test pattern. I want to serve better 10,000 than 1,000 customers, because this way you get quality. You need many, many, many customers and their issues, much more than the big wafer suppliers have. Then you can come up with patterns that are really relevant to those customers. A lot of customers today have signal integrity issues. Also, if the tester has any issue, send it back to us. It's a small test system, only 10 kilograms. You don't need big maintenance. Send it back to us. We will fix it. We will improve it. You get it back. So this is the real vision I have in mind. Share our technology with others. Pay a fair price per use. Give us as much feedback as possible. Better 10,000 customers than 1,000. And come up with an industry test solution which is as wide and as profound as possible. Very different approach than today, where everything is confidential, not shared, and where you only serve a small amount of customers with your solution. So this is our vision, and if you have any questions, please raise them now.
All right, thank you, Peter, for that detailed and really interesting presentation. I learned a lot. We have several good questions from our audience. Are you ready to answer some of those?
Sure, you're welcome.
Excellent. All right. So the first question says that you mentioned in your presentation that you want to spend 12 hours of testing instead of 20 minutes today. Why does this help?
With this tester, I could run a lot of interesting experiments. $5 million tester is too expensive to do an experiment like test for 1 week a couple of thousand of components. And unfortunately, our technology is going towards 10 nanometer in the DRAM domain. They are dirty. A lot of things happen. Some things suppliers very fierce, for example, copper ions in silicon.